Okay, so we're going to have a few lessons now on the topic of multivariate calculus. And so that just means the calculus of functions of several variables instead of just one variable. And the good news is you already know almost all you need to know for multivariate calculus. All of the ideas from single variate calculus go through. There's just a few kind of additional issues that arise when we're working with functions of several variables that I'll talk about, but honestly, this is a good chance to reinforce some of the concepts that you'll remember from univariate calculus. Okay, so just what do I mean when I say univariate? Contrasting it to multivariate. Univariate calculus, we had y, let me give myself a little more space to write here. Y, our range variable, our dependent variable, if you want to think about it that way, is a function of just one variable. In the multivariate case, we're going to say that y is a function of several x variables up to n there. So we were kind of doing that implicitly in our matrix algebra lessons. Those were linear functions of several variables, but just as with univariate calculus, the linear functions are a subset of broader functions here. But the calculus part of multivariate calculus is going to allow us to think about functions of several variables where the relationships are more complex than linear. So again, kind of thinking about what we were doing unselfconsciously when we were thinking about linear functions, y as a function of x1, x2, x3, when we were thinking about the impact of one of the x variables on y, we kind of implicitly held the other variables constant. That's a very natural way to think about how one thing affects another, even though it's not the only thing that can affect the dependent variable. And that's the idea at the heart of multivariate calculus. Okay, so if we want the equivalent of the derivative in univariate calculus, what we have on the multivariate side is a partial derivative. And it's a partial derivative in the sense that we're changing part of the set of domain variables and holding all of the other constant. So we're thinking about the impact of a small, infinitesimally small change in one of the x's, x of I, on y, holding the other x's, the x of j's, constant. And we write it a little bit differently. Okay, so the partial derivative, instead of those Roman dy dx's, we use kind of a funky version of a lowercase delta, and people always just say del. Okay, so it's del y, del xi. Okay, so just emphasizing the little del's there indicate that we have a partial derivative, that there are other variables that we're holding constant. Okay, so we're looking at the impact of one of the x's, and all of the other ones, we're just treating them like parameters. Okay, we kind of did that a couple of times in univariate calculus. In one of the workshops, we took a bunch of derivatives with respect to x, and then I said, okay, now take a bunch of derivatives with respect to y. I think it was like u equals a function of f of x and y. So, you know, whether a variable is a parameter or a variable, or I should say whether a symbol that can represent a number, let's be precise here, is a variable that is varying or a constant that is constant is completely a matter of context, and we can switch up the context however we want to, and that's what we're just kind of doing more explicitly in multivariate calculus. Okay, so I'll do an example in a minute. One thing I just want to add here on the setup, nomenclature, symbols side of things, you can also have the F prime notation for partial derivatives. So often we just write it as a subscript. Okay, so this subscript here is telling us take the partial derivative of f with respect to the first variable. And we often write this when we want to sort of emphasize that it itself is a function of those variables. Sometimes, so this would be the partial derivative with respect to the first domain variable. Sitzeder and Hammond like to put a prime in there as well to kind of really hammer home the point that yes, we're taking a derivative here. A lot of books don't do that. They just rely on you seeing the subscript and kind of knowing that we're in the type of problem where we're taking partial derivatives. That's what it is. But you can use that notation when it's helpful for you. Okay, so let's just look at a function here. So let's say we've got y, and it's going to be a function of two variables, x1 and x2. And let's say it's the log of 3x1 plus 2x2. Okay, let's find those partial derivatives. So f1 is del y, del x1 here. And what did I say I was going to do? If I'm taking the derivative with respect to x1, I'm going to treat that x2 just like it's a constant. Okay, it could be a number, and that is not just what we're doing kind of computationally, it's what we're doing logically in our minds. If I keep the x2 constant, I'm not letting it change, how does a change in x1 affect my y variable? Okay, so just take that derivative the way we always have. It's the derivative of the outside here. I've got the log of something, so that is going to be 1 over that something, 3x1 plus 2x2. But then I also need the derivative of the inside. It's a chain rule thing because I've got a nested function, and the derivative of the inside with respect to x1 is 3. That's my partial derivative. And of course, I could take a partial derivative with respect to x2 as well. And now if I'm taking the derivative with respect to x2, I'm holding x1 constant. So that's my partial. You guys would not normally be writing out the f2 equals del y del x2. You don't need to do that. It's totally redundant. I'm just doing it here because I'm thinking that the notation might be new to some of you. So let's overdo it a little bit. Anyway, so taking the derivative of this thing with respect to x2, I treat x1 just as if it was a number there. So it's, again, the derivative of the outside. Log of something is the derivative of log of something is 1 over that something times the derivative of the inside. And the derivative of the inside now is 2 because I'm differentiating with respect to x2. Great. So a thing that you'll notice here is that just as with regular derivatives, just as with univariate derivatives, the derivative is itself a function. In this case, it's a function of those same two variables. So that's worth noting here. This is a derivative of x1 and x2. So the impact of x1 on y depends not only on what value of x1 we're at, generally true for a nonlinear function, it also depends on what value of x2 we're at. And same deal with f2. It's a function of both of those variables. Okay. It's a little hard for some people. I'm not a super visual person, as you're going to see in a minute when I try and draw a picture. And it can be a little hard for some people to visualize multivariate functions. Some people are really good at it. And if you are good at it, I know it's a powerful tool. So I'm going to sort of attempt to set you down that path here. So the way, a way to translate these functions where you really need at least 3 dimensions into 2-dimensional drawings is to kind of think about slicing them different ways. So what am I saying here? So if we really have y, x1, and x2, what we need are 3 dimensions, one for x1, one for x2, and one for y here. But what we can do is, again, we can hold one of those things constant, and whichever one we want, we can hold constant, and then think about slicing the 3-dimensional function at the different values of the thing that's being held constant. Okay, so let's, easier to just show than to talk about. So let's think here. I'm going to use 1 dimension on the paper to be my range variable y, and I want to look at the effect of x1 on it. So now you can think about the, so here's my y, here's my x, think about x2 is kind of coming out of the page here, and then you can slice the function that's parallel to the page. You can take parallel slices to the page at different heights above it. Those correspond to different values of x2. Okay, so let's say that right at the page where x2 is 0, x2 equals 0, that's one contour here. Go a little bit above that and slice the function at x2 equals 1, and you'll get a slightly different shape. This is the point I'm saying here. x2 equals 1. And the thing I want to emphasize here is we take a particular value of x1 here, x1 bar, and yes, the slope of the tangent line is different. So this tells us the slope of that tangent line is the first derivative of f, y equals f of x1 and x2, evaluated at x1 bar, this x value, and x2 equals 0. Here, put that to my pen, we have that same first derivative evaluated again at the same x1 value here, but now x2 equals 1. Okay, so this is just like I warned you, not a great picture, but a way to sort of envision how the slope, the effect of one variable, the slope at a point, the first derivative, depends on the other variable. And of course, like always, the slope of x1, the effect of x1 on f also depends on what value of x1 we're at. If we go up here, different value of x1, the slope's going to change as well. Okay. One more thing one more sort of basic thing to talk about. Actually, let's go back. When I took these derivatives, I'm using the same rules of derivatives that we used for univariate calculus. All those rules just completely go through. It's just a matter of, which variable you're letting vary and which ones you're treating like a constant. So 0 new things there. The only rule that changes somewhat is the chain rule. When we have multiple variables and nested functions, there's more to keep track of, okay? And the chain rule is going to help us keep track of that, okay? So we're going to have a multivariate chain rule. I'm just going to write it out for a function of two variables here, I think you'll see how it generalizes in a really obvious way to more than two. So multivariate chain rule. So again, we've got y as a function of x1 and x2, but now we're also going to have x1 be a function g1 of u1 and u2. So everything's multivariate now. This sounds like social science, right? Everything depends on a bunch of other things that depend on a bunch of other things. And that's why the world is complicated and why we have to work so hard to understand it. So x1 is a function of the two u variables, and I'm going to have x2 be a different function. Okay, so I've got subscripts on my functions here of those same two variables. And suppose I want to know the partial derivative of y with respect to u1. Okay, so this variable, how is it affected by this u1 that affects y through both x1 and x2? Well, I just kind of gave away the answer there. It means if I want to know the effect of u1 on y, I have to think about both how u1 affects y through x1 and through x2. And it's standard chain rule logic, but now it's kind of got two parts. Okay, so the first partial derivative of y with respect to u1 is the derivative of y with respect to x1 times the derivative of x1 with respect to u1 plus the derivative of y with respect to x2 times the derivative of x2 with respect to u1. Make that subscript a little bit clearer here. So what I'm looking for is this affected kind of a low-level variable on the high-level variable. I have to account for all the paths through which u1 can affect y. So there's this path that goes through x1 and this path that goes through x2. Didn't mean to erase there. x2 del. Rewrite that thing there. x2 del u1. Okay. When you're doing chain rule things, if you feel like it's getting a little bit complicated, you can always help yourself out by drawing a little picture. Here, if you have like y is being affected by x1 and x2. And these guys are being affected by u1 and u2. One is affecting both x1 and x2. u2 is affecting both x2 and x1 here. And if you do it this way, want to think about the effect of u1 on y, you just sort of trace all the paths. What are all the paths that start at u1 and end at y? Okay, well here is one that goes through x1 here, and another light color here, and here is one that goes through x2. Okay. And each partial derivative that's being multiplied here is one step in the one link in the chain, so to speak. Okay. And you can imagine generalizing this to, x1, x2, x3, u1, u2, u3. You also don't have to have all the functions having all the intermediate variables depending on the same lower level variables. You could have some of these first derivatives be 0. Okay. One kind of side comment I want to make here, you might be noticing already that in multivariate calculus, just like in linear algebra, there's a lot going on in the subscripts. And I want to flag this as something that I know it's a cognitive burden on you as a reader, a student, and a modeler to be thinking about all these subscripts, but they're there for a reason, okay? So if you find yourself reacting like, subscripts are those things that I hate, kind of step back and take a deep breath and ask yourself, what are you really hating there? Are you hating the subscripts? Or are you hating the fact that it's a complex situation? The subscripts really themselves are not creating complexity. It's a way that we try to help ourselves manage the complexity. So they do have their disadvantages. I have that kind of frustrated attitude sometimes too, and it's certainly an easy place to make mistakes when you're calculating. Write the wrong subscript there and uh, get yourself confused that way. I've been there many times. But again, the way to manage that is to step back, recognize the use that those subscripts are, the useful role that they're playing, and maybe give yourself a couple minutes to sort out what they might be meaning. We use them for different things. We use them sometimes to indicate partial derivatives. Here, you might be noticing that's not a partial derivative. Unfortunately, I'm doing that as to denote different functions here. Not great notation, but might be the right thing to do in this context. So I think that's all we need to say in this video. The main point of this video is just to sort of emphasize how almost all of what we do in multivariable calculus is the same as what we do in univariate calculus. And that's going to be the theme that's going to go through the remaining lessons in this unit. So I'll see you in the next one.